Hello and welcome back to yet another episode. Myself, Fazira Razak Hamza, PG Department of Computer Science, and I'm here to present on the course Computer Graphics. So in the last episode, we were discussing about area filling algorithms. So today in this episode, I'm going to discuss on transformations, that is geometrical transformations. So let's see what is geometrical transformation. So transformation, the word itself, we know that we are changing something or transforming. So let's see what we are transforming in geometrical shapes. So when visualizing an object, it is desirable to scale, rotate or translate the object. So basic 2D transformation simulates the movements. When visualizing an object, it is desirable to scale, rotate or translate the object. So general procedures for applying translation, rotation and scaling parameters to reposition and resize two-dimensional objects. So basic 2D transformations simulates the movements and manipulation of objects in the plane. So it is basically used to change the shape, size and orientation. So there are, let's see, transformation equation can be expressed in a matrix formulation that allows efficient combination of object transformations. So we are finding out transformation equations in a matrix format. Now there are three basic transformations. They are translation, rotation and scaling. Along with which we are studying also an additional two additional transformation, that is shearing and reflection. So this is how the transformation in computer graphics looks like. Now let's move on to translation. So translation is applied to an object by repositioning it along a straight line path from one coordinate location to another. We can translate a 2D point by adding translation distances, that is dx and dy, to the original position x, y to move the point to the new position x dash, y dash. So therefore the equation looks like this, that is, this is x dash is the new coordinate position. So x dash is equal to x plus dx and y dash is equal to y plus dy. So the translation distance dx dy is called translation vector or matrix. Now the equation will be like p dash is equal to p plus t, where p dash is equal to x dash y dash, p is equal to x, y and capital T, which is the translation vector or matrix, which is equal to dx dy. So this is what I said, we will formulate a matrix of the equation. So this is the matrix representation for translation. Now this is how the translation figure looks like. This is the point P and this is the point P dash and this is the translation vector or distance capital T. Now let's see, translation moves objects without deformation. That is, every point on the object is translated by the same amount. Now we can see an example. We have given a line as a geometrical shape here with P as 4, 5 and Q as 7, 5. Now given the translation vector that is 3, minus 4. So after translation P dash coordinates becomes x dash is equal to x plus dx, that is x is 4, see here 4 and translation vector dx is 3. So 4 plus 3, 7 and here y is 5 and the translation vector is minus 4. So 5 minus 4 which is 1. So we get the value 7, 1 for P dash and for Q dash the coordinate is 10, 1 and this is how we have translated it from PQ to P dash Q dash. So this is how translation works. Now let's move on to the next topic or transformation, that is scaling. Scaling transformation alters the size of an object. So it is carried out for polygons by multiplying the coordinate values x, y of the vertex by a scaling factor Sx, Sy to produce the transformed coordinate x dash y dash. That is, x dash is equal to x into dx and y, sx, and y dash is equal to y into sy. So the transformation matrix for scaling is given by x dash y dash is equal to sx0, 0 sy into xy, which we can say that p dash is equal to s into p. So the values of sx and sy can be any positive numeric values. We can say that if sx equal to sy, then it is called uniform scaling. Else, if sx not equal to sy, it is called differential scaling. There is also one other condition, that is, if sx and sy are greater than 1, then the resulting size would be larger and away from origin. Now let's see an example. Scale the object with coordinates A21, B23, C24 and D44 with the scale factor of Sx equal to Sy equal to 2. So here our Sx and Sy is equal, so we call it as uniform scaling. And one more condition, Sx and Sy is greater than 1, then the resulting size would be larger and away from the origin. Now we'll find out the new coordinate positions, that is A dash, B dash, C dash and D dash. So we got A dash is 4, 2, B dash is 4, 6, C dash is 8, 4 and D dash is 8, 8 by using the equation x dash is equal to x into sx and y dash is equal to y into sy. So now after scaling, the image will be like, so this is the original image A, B, C, D. Now it is double the size after scaling and also away from the origin. So this is how scaling works. So the effect on the object is that the object is doubled and shifted away from the origin. Now let's see the next transformation, that is rotation. A 2D rotation is applied to an object by repositioning it along a circular path in an xy plane. So to generate a rotation, we must specify the angle of rotation theta and the position xr, yr of the rotation point, which is known as the pivot point, about which the object is rotated. So let's see the figure. This is how the figure looks like. This is the pivot point xr, yr, and this is the angle of rotation theta. This is the original image and this is being rotated along with the angle of rotation theta, and this is the new coordinate position x dash y dash. So let's see how the transformation of rotation of a point P when the pivot point is the origin itself. Okay, let's see. Rotation of a point from position xy to position x dash y dash through an angle theta relative to the coordinate origin. So the original angular displacement of the point from the x-axis is actually phi. Now let's see how it works. So there is no pivot point here. It starts from the origin itself. This is the original angular displacement phi with the original image, and we are rotating it to an angle theta and transforming it to this side. Okay. X dash y dash is the new coordinate position. So here theta is the angle of rotation. So it takes positive values for counterclockwise rotation and it takes negative values for clockwise rotation. Okay. Now phi is the original angular position of the point P from the horizontal. R is the constant distance of the point P and P dash from the origin. So from this figure we can find out sine phi, where sine phi is equal to y by r. Similarly, cos phi is equal to x by r. From this equation, we can find out the value of x and y, right? That is, x is equal to r cos phi and y is equal to r sine phi, which is marked as equation 1. Similarly, we can find out x dash and y dash. X dash is equal to r cos theta plus phi and y dash is equal to r sine theta plus phi. And I'm expanding the cos theta plus phi and sine theta plus phi. So we get the value of x dash and y dash as x dash is equal to r cos theta cos phi minus r sine theta sine phi. And y dash is equal to r sine theta cos phi plus r cos theta sine phi, which is marked as equation 2. Now, when we substitute 1 in 2, we get x dash is equal to x cos theta minus y sine theta and y dash is equal to x sine theta plus y cos theta. This is our equation for finding out the new coordinates of rotation. So x dash y dash is equal to cos theta minus sin theta cos theta into xy. That is P dash is equal to R into P. Now let's see an example of rotation. Consider an object, a 90-degree rotation of object A11, B101 and C55 in counterclockwise direction and give the new coordinates. So, x dash is equal to x cos theta minus y sin theta is our equation, and y dash is equal to x sin theta plus y cos theta is another equation for finding out the new coordinates x dash and y dash. Now theta is 90 degree in counterclockwise direction, so we have positive values for theta. Now I'll find the new coordinates. A11 becomes A dash minus 1 comma 1 and B101 becomes B dash minus 1 comma 10 and C55 becomes C dash minus 5 5. So after rotation, the figure will be like this. This is the first image is the original image and we have rotated it 90 degrees in counterclockwise direction. So this will be the position of the figure after rotation. So this is how rotation works. Our next two topics, that is shearing and reflection, will be discussed in the next episode. I hope you all understood this episode topics. Thank you. Thank you so much.